Chemical Foundation of Life, Chapter 2, Part 3. How do atoms form molecules? Well, we're going to link atoms together using structures called chemical bonds. Chemical bonds help to link atoms together, but it's not all the same. We have three types of chemical bonds that we need to learn about: covalent, ionic, and hydrogen bonds. For covalent bonds, electrons are shared. And here we see an illustration of two atoms of hydrogen and one atom of oxygen, H2O. And notice we're going to combine those atoms of those two different elements together in a chemical reaction to produce H2O. And notice the electrons of the oxygen are illustrated in red, and the electrons of the hydrogen atoms are illustrated in white. Well, they're not really those colors, but this is to give you an idea of how covalent bonds are sharing electrons between different atoms of either the same or different elements. So, electrons are shared between atoms, and these are the tightest, strongest bonds that we can find in nature. For covalent bonds, we can have the sharing of one pair of electrons between two atoms, two pairs of electrons, which are called double covalent bonds, and we can even find triple covalent bonds in the universe. But for organisms or biological systems, it's only either single or double covalent bonds that we might find forming molecules. Covalent bonds might find that the electrons are unequally shared based on essentially the electronegativity of a particular atom. Electronegativity means how many protons are in the nucleus of that atom, how many electrons are surrounding that atom. And if we take a look at the electronegativity and the arrangement of the atoms around the oxygen to form one molecule of water, we find that the oxygen has a higher electronegativity than the hydrogen atoms, which means the electrons that are shared from the hydrogen atoms are actually going to spend more time surrounding the oxygen atom than they would if it was simply separate individual atoms of hydrogen. Since the electrons are spending more time around the oxygen, we see that there's a Greek symbol, delta, a lowercase delta, and a minus sign. There's a slightly elevated or increased negative charge because the electrons shared by the hydrogen atoms spends more time floating around or surrounding the oxygen atom. On the other hand, if we take a look at the hydrogen atoms, the electron spends less time surrounding those nuclei, and so we see a slight positive charge. That's the delta plus. You see a sign to each hydrogen. These are described as polar covalent bonds. In other words, there's a slight negative charge, there's a slight positive charge on some of the atoms in the structure. These positive and negative charges, whether they're partial, illustrated by the delta plus or delta minus, or if they're full negative or positive charges, are how different atoms within different molecules interact with one another. The actual geology or the geometric shapes of the molecular structure is illustrated with what's called a bent molecular shape or configuration for water. It's not really a 90-degree angle, it's actually 108 degrees, a little bit splayed apart. If we take a look at the molecular structure or rearrangement for other molecules, we find that the tetrahedral or the linear arrangement doesn't always lend itself to the formation of polar covalent bonds. because some atoms are not nearly as electronegative as others. If we take a look at the polar covalent arrangement between carbon and oxygen for carbon monoxide, there's a little bit of a polar covalent bonding illustrated in the lower left-hand corner. Compare that to carbon dioxide, which has a linear arrangement. That's a nonpolar covalent arrangement because the electronegativity is kind of balanced out and distributed in a linear fashion. Nonpolar covalent bonds, in which there's an equal sharing of electrons, is going to give us those nonpolar covalent bonds. Very sort of non-interactive. Methane is a good example, illustrated in the middle, with this tetrahedral. Again, nonpolar arrangement, sort of equal distribution of electrons all the way around these different atoms, and the linear structure of carbon dioxide, where any of the electrons are essentially separated far enough apart that they're not going to form any kind of polar or slight positive or slight negative charge between each other. An example of mixing polar compounds with nonpolar compounds or molecules is when we mix oil and water. Oil is nonpolar. We'll talk more about oils later as we proceed through this chapter. Water, on the other hand, is a polar molecule or compound. And so water and oil, the polar water and the nonpolar oil, do not mix. And that's a driving force in the formation of structures of all kinds of biological systems. The interaction of polar and nonpolar molecules and compounds really is at the core of how different biological systems and structures within those systems interact. Ionic bonds are the type of chemical bond where an electron is transferred from one atom to another. And notice what happens. We actually change the name of the description of a particular element. On the left, we start out with one sodium atom and one chlorine atom. Because of the rule of octet, notice that sodium has one lonely little electron in its valence shell, whereas chlorine has 7. Well, ideally, we want to have a nice full, valence shell, nice intact valence shell. So, notice that the sodium atom transfers its electron to chlorine. We wind up with a sodium ion. That means an electron is missing from the outermost shell, and the corresponding positively charged proton in the nucleus of that sodium atom no longer has its negatively charged counterpart. So we describe this as a positively charged cation, or sodium ion. On the right-hand side, chlorine has accepted that extra electron donated from sodium, and now we call this a chloride ion, or negatively charged anion. An anion is an atom that has accepted an electron and is negatively charged because that has that extra negative charge from that donated electron. A cation is an ion that is missing an electron. The formation of ionic bonds is important in a variety of chemical systems, including the importance of ionic bonds in organisms. Here's an illustration of how ionic bonds form, using sodium and chlorine as an example. Again, notice that the charge on the illustration of these atoms changes from just straight sodium and chlorine to Na plus and Cl minus, or a sodium ion and a chloride ion. Some other interactions that do occur that are important for us to describe and talk about are weaker interactions. Those are hydrogen bonds and van der Waals interactions. Ionic and covalent bonds are going to require energy input to break those chemical bonds. Hydrogen bonds, on the other hand, are weak interactive charges and attractions between separate, different molecules. And they're weak attractions or weak positive and negative charges on different separate molecules that are going to loosely hold structures together. And these weaker forces, we call them weaker intermolecular forces, are very important in biological systems. Hydrogen bonds are very important, as are interactions called van der Waals, which are the weak attractions or interactions, just simply due to changes in electron density. There are other types of weak interactions that you might hear about perhaps in a chemistry class, but for us, really it's covalent, ionic, and hydrogen bonds that are the most important to describe and talk about in biology.